Hey robot makers, hope you're having a good day so far. So let's get over to our live stream and make it a bit of a start, shall we? So do you want to learn about the differences between MicroPython running on an Arduino and Arduino running C++, and the differences between the two? Then this is the ultimate Smackdown. This is the show for you. Let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. We've got my air horn ready to go here. Right. Okay, is that deafened everyone? Okay, let's get over to our slides and make a start, shall we? So yes, today's show is sponsored by PCBWay. I've been making a whole bunch of PCBs, which I've got just over here, which I'll be looking to put on the store once I've sorted out some shipping issues. So yes, these are made from PCBWay. These are some very simple PCBs. You can see that this one's made for the Raspberry Pi Pico. Pico W, and this one can be very easily made into a game controller with lots of different controls. So yes, I got these through PCBWay. I think it took about 2 weeks from designing it to them receiving through my house. So a fantastic service there. We can have a quick pop over and have a look just very quickly how easy this is to do on PCBWay. Here we go. So load up the browser there. We can quickly go to an instant quote if we know what the size of our boards are going to be. So let's say 10 by 15, and we need, say, let's go for 5. That's a minimum kind of quantity to get these manufactured. I'm just going to put that on mute for a sec. And I'm going to go with the regular kind of green. I think that's the cheapest one to go with there. So if I now just click on the calculate button there, we can see to get these made within the next 24 hours, it's just $5. So that's $1 per board. And the shipping is only going to be $3.74. You can get it quicker if you want. You have to pay a little bit more for that. But I find this is a fantastic service, and I've tried quite a few of the PCB manufacturers out there. The PCBWay are my personal favourite. Okay, let's get down to the Smackdown, shall we? So let's have a look at the differences, first of all, between compile code and interpreted code, because this is the main difference between, say, MicroPython and Arduino running C++. So on the Arduino C++, and some Arduinos can run MicroPython as well. We'll get over to that in a second or two. So on the plus side, it's very efficient use of memory. It detects errors at compile time. So when you're writing your code, it can actually detect the kind of errors that you'll come up against at that point. And it runs code very, very fast. So if you're doing something that's very performance critical, such as camera, image processing, that kind of thing, then C++ is definitely the way to go. And there's also a large collection of drivers and libraries that are available through the Arduino IDE as well. On the sort of con side, memory management requires a couple of extra steps to release memory. If you're doing things that require more memory than your controller, your microcontroller has, you have to do some quite careful memory management stuff there. And you can lead to memory leaks if you don't get that right as well. Every change needs a recompile, so this can take up to a minute every time you make a single change to your code, recompile it, upload it, and then try it out again. So the development cycle can actually be quite elongated with C++. And the compile code is not portable between platforms. So if you want to try running the code, the hex bin file, whatever it is, on one microcontroller, you can't just drag and drop that over to another one and it run. We can do that with MicroPython. And it's more complex as a language for beginners. A lot of people find issues with this when they're sort of learning it. Let's have a look at MicroPython next. So with MicroPython, there's no need to compile your code or recompile it. Changes run immediately, and this is one of the best reasons, I think, to run MicroPython on your microcontrollers. So this quicker debugging and development cycle means you can get your projects up and running so much faster. And it's a simpler language to learn. A lot of beginners like MicroPython because it's so much simpler to get up and running. And the code that you write is portable between all platforms, and that's the code that runs on the device. So there's no need to compile it for a specific platform. It just runs straight off the file. On the con side, so there is a growing collection of libraries and drivers. Not as many perhaps as in the Arduino space, and that's because there just needs to be a lot more focus on the Arduino platform than there has been traditionally for MicroPython. MicroPython does use more memory than C++ for similar kinds of projects. We can have a test of some of these later on. And it's not suitable for all real-time tasks such as image processing. It can be quite a bit slower for those things. We'll get some numbers to see exactly what that looks like. And the errors are actually detected at runtime. So your code, you can type it in, you'll not get any errors there. When you run this, it might run fine. And when it gets down to that line of code that's got a bug in it, that's where the error will show itself. So the code does run that bit slower. Well, like I said, we will look at the numbers in our Smackdown in a minute or two. So let's have a look at the mechanics of how compiled and interpreted code works. So compiled code requires more preparation, but once you've completed it, runs faster in less memory. So MicroPython itself is actually written in C++. So that tells you, just as an idea, the sort of levels of complexity there. Interpreted code is quicker to develop, and the overall time to create code in and debug it is much lower, so it's much quicker to do that. And you tend to write more code than you read more code than you write, so making sure that this code works well and is easy to read is actually quite important. And some interpreted language output to bytecode, which can run on a virtual machine. MicroPython, I believe, does this as well. I know Python does. So there's an extra step there where it actually outputs this kind of intermediate code. It's as if there is a processor that's being emulated on the microcontroller. And that makes it portable between different platforms as well. So let's have a look at a very quick overview of the compilation process. So the source code, we write our Arduino code, I call it Arduino code, it's C++, and I say that, and it's actually a different language completely. It's called processing. So one of the reasons when you write an Arduino sketch, it's called a sketch and not a program or a script, is because the original language it was based on, processing, was designed for artists and artisans, and they would sketch things, they would put things together in that kind of artistic way. So Arduino C++ is actually based on processing, which in turn is based on C++. So we get our source code, we do some pre-compilation of this, we pre-processing. What that means is it will look through all the different files that you include in your project. It will assemble all those into one single file. Then it will compile that code, and what that means is it will look through each line of code, it will evaluate and turn those things into symbols. Those symbols then get turned into assembly language. We can have a look at some assembly language shortly as well. And that's the compilation stage. The assembly language can then be assembled into binary for that particular platform. You get an O file, an output file, or object file. The linking stage is where we take the object file that we just created, and if we have any other libraries, we will take the object file for them and take the bits of code that we need from them libraries and bake it into one single executable file, a binary file, and then uploading it into our device, and then we can run it on our device. So they're the different stages of compilation. It's quite a few different steps. The linking one I think is always interesting, because unless you know computer science, that might seem a bit unusual. And these are statically linked, so we will have a library. We'll take the object, the code from that particular library, and we'll put it into our file, and it stays that way. On Windows and macOS to a degree, you can have dynamic link libraries, or DLL files, so the code can actually change in them, and it will, at runtime, it will actually link the file into the executable. So that's why on Windows you have all these .dll files knocking about there to do with that linking stage of the code. Let's have a look at the compile code. So we've got some source code here. You can see on the right hand side there, this is a little distance finder for a ultrasonic rangefinder written in C++ for Arduino, and this is the human readable form of our program. We can put comments on there, we can structure it in a way that makes sense to us, and that's the code that we are kind of most familiar with. It consists of these high level instructions written in C++ to define what our program does, and you define these functions like setup and loop for Arduino to set variables, apply control structures like if else loops, etc. And that's what makes up our program. Next step is the pre-processing. So we'll take those things like define, or the H files, the include files, and they all get assembled into a single output file, a new C++ file that has all those macros being replaced by actual values. So when we say define echo 8, for example, echo pin will get defined as a, you can imagine it's like a constant with the value 8, an integer 8, because it's not a floating point, it doesn't have a 8.0 or anything like that. So the pre-compilation will interpret that and create a symbol for that. So everything gets changed into symbols rather than nice words. A symbol is simply just like a variable that has a particular reference, a unique reference, but isn't necessarily the word that we created there. The next step then is compilation. So the compiler will translate our pre-processed code into assembly language. So we end up with a .asm file. If we were to have actually these files on our file system, we could see them individually. A lot of these things happen all in memory now, so you don't actually see the individual files. And the assembly language is a low-level human readable. You can read and write assembly language, as we will do shortly. And that's specific to the architecture of the particular microcontroller. So it might be the AVR or ARM or whatever kind of processor that we're using. And the compiler will also perform some error checking and optimization at this stage. So it might actually not order the code in the order that you want it to. If it knows a particular piece of code takes longer to run and it isn't dependent on other pieces, it can put that further up the chain, have that run, and by the time you come down to another piece of code, that result is ready, for example, on a sort of multi... you can have things running at the same time in processors. So again, the compiler will check for errors and optimize, and if there's any errors, they were caught at this point. Next up is assembly. So this is where we take the assembly language, and assembly language can pretty much be one-to-one converted into machine code. These are the ones and zeros that run directly on your processor. So these binary instructions that the microcontroller could understand are executed directly. So that the result of this converting to machine code is an object file, a .o file. This contains all the translated binary files for your program, but it's still incomplete because it doesn't have these external references to libraries, for example. Next up then is linking. This is where the linker combines all the object files from your code from the external libraries and dependencies into a single file, which is an executable binary file. It resolves any function calls to these external libraries, these variable references across multiple files, and ensures everything is in correct memory locations for execution. And the final result is a complete binary file, or .hex. You might see that if you ever write code on a microbit, you see a .hex file, a .bin or .elf. They have different names, but it's all just machine code for that particular microcontroller. And then we can upload that into the microcontroller, which is the next step there. So we use a tool like Arduino's IDE. There's other tools as well, like ESP tool you can use to upload code to your ESP32, and then that's ready to run on the microcontroller on the next time it gets booted up. And then executing it, so the code that's ready to run on your microcontroller will start whenever you apply power to it. And it simply follows the instructions line by line with the hardware, such as sensors, LEDs, motors and so on, just like your code, but all been translated from that human readable all the way through to this machine code. So that's how we compile code and all the different steps. That'll become just relevant as we do some testing in a minute or two. So if you like what I do and you want to do more videos like this, if you want me to make more kinds of MicroPython videos, give me a thumbs up, drop me a comment what your favourite microcontroller is. I'm interested to know, is it just all people loving the ESP32? Do people love the Raspberry Pi 2, for example, the Pico 2? What's your sort of microcontroller of choice? And of course there's a microbit as well. And if you haven't subscribed, please consider subscribing. It means an awful lot to me. It doesn't cost you anything and it helps the channel to grow as well. I do go live every single Sunday at 7 o'clock BST currently. We're in British summertime. So yeah, if you want to hang out with me, you can do that live as well. Let's see how many people. We've got 72 people watching currently. Okay, interpreted code. This is a different approach. This is what MicroPython does. So we start out with our source code. Looks kind of similar to C, C++, but it's a lot easier to read, certainly a lot easier to write. Similar kind of high-level instructions written in MicroPython to define what a program does, and we define functions like def main, we set variables, we apply control structures. And unlike the Arduino, we don't have fixed function names like loop and setup. We can just define whatever we want and it will just run the code top to bottom. So that's how we write our code. The next step is the interpreter. So the interpreter will every single line it will evaluate, it will then create machine code directly for your processor, or in the next step it can actually translate that to bytecode, which is this intermediate level code. And unlike compile languages, there is no separate compilation step. We can just change our code and have it immediately run one line at a time. So it's very, very simple, very conceptually simple for us to get this up and running. So the bytecode step, some MicroPython implementations can convert source code into bytecode, a more compact intermediate form of the program, and this step can optimize execution. Single bytecode is faster for interpreted to process rather than the raw source code, so it's done that kind of converting things into symbols already for us. And bytecode is platform independent, meaning it can be interpreted across lots of different devices with a MicroPython virtual machine. Bytecode is stored in the .mpy files for efficiency. So you might have seen some of those. Then execution, MicroPython runs on a virtual machine which simulates all the a small CPU in the microcontroller, and the virtual machine executes either the bytecode or the raw Python code directly. The VM is responsible for handling all the low-level operations such as interacting with hardware, the GPIOs, sensors and pins via the MicroPython's standard library. And during this stage the code actually affects the hardware, such as turning lights on and off and reading data. So my personal favourite here is MicroPython. You might get to see that through this program. So unlike compiled languages, errors are detected at runtime. So if there's a logic error, such as trying to access a non-existent hardware pin or using an undefined variable, it gets reported by the interpreter when it reaches that line of code. So runtime can be displayed immediately, allowing you to debug and fix problems in real time. So Arduino boards that support MicroPython, there's a growing number of boards. So we see the Arduino Nano BLE, which is Bluetooth Low Energy, the Nano BLE Sense, the Nano BLE Sense Revision 2. There's also the Arduino Nano RP2040 Connect, the Arduino Nano ESP32, which I have over here. So these are, I think, my favourite Arduino boards at the moment. They're nice and compact. They run MicroPython, and they can also run the C++. There's also the Nicola Vision. We have the Giga R1 Wi-Fi, the Potentia H7, Potentia C33, and there's also the Arduino R4 Unos as well. So let's have a demonstration, shall we, of a rangefinder example. I've actually not got a rangefinder plugged into any of these at the moment, but we can basically just run the code and see how the kind of differences are. So let me just get my environment ready here, and we can have a look and see the kind of differences between the code between the two. Right, so if I come over here, let's see if I was hoping to get these side by side. Maybe if I do, let me see if I can get these side by side. Let's do the primary display. There we go. So on the left hand side here, this is the Arduino IDE. On the right hand side is the Arduino Lab for MicroPython, which is another piece of software that the Arduino team have written for writing MicroPython onto your ESP32 Nano, for example. So over here, this is the Arduino IDE. I've got the Arduino Nano ESP32 plugged in. It's connected to one of the ports on there. We can plug that in. I think actually at the moment that one is plugged in to the MicroPython board. Let me just very quickly swap that over. If I just show you on my desk over here, I've got two Arduino ESP32 Nanos. That one is running MicroPython, this one is running C++, so I've just quickly sort of switched that one over there. Okay, but if we get back over here, I've now connected up that Arduino Nano ESP32, and you can see there it's plugged into that particular serial port. So we've got a whole bunch of variables here: start time, end time, current time, calculations, and so on. So this example I've got up here I think is like a speed test, but let's actually go for the well, let's do the speed test. I said rangefinder, we're going to do a speed test instead actually. So the start time and end time is just going to be a long number, which is the number of milliseconds since the device was switched on, and the start time is when we're going to start the clock, we're going to run some code, and then we're going to stop the clock. So the start time and the end time are going to capture those values. The current time is just what the current time is, because we're going to run this for a number of seconds. The calculations is how many calculations we can do per second, so we're going to store that in there. And the total calculations is, if we run this for say 3 seconds, what that total number of operations that we've done is. So we've got this void setup. So this is a special function that all Arduino programs have, which is to set up your variables, which you do once when the program runs. So we're going to say serial.begin 9600. That sets up the serial console, which is down at the bottom here. And we say starting C++ calculation test. We've also got a delay there of 2000 milliseconds, I think it is. So that's essentially like 2 seconds, just to give the console time to sort of set up. Then we've got this run calculations for 3 seconds loop. So we have to define in C++ what type each variable is. So we want a variable that's called second, and it's of type integer. We're going to make that start at 1. We want it to stop when it reaches 3 seconds. So as long as this is like the finishing condition, second is less than or equal to 3, and each time we go around the loop, we're going to increment that loop. So we're going to increment it by 1 second. So second plus plus just means add 1 to the variable second. Then we've got this curly brace. So these curly braces are kind of paired. You can see that there's another curly brace down here that matches that one. We have got some other curly braces here. If I click on them, you can see it kind of highlights the pair there. So we set the calculation to 0. Let's reset the number of calculations. Let's grab the current start time. So millis is a function that grabs you the current millisecond tick that's going on. There's like a little internal clock. We can grab that number of milliseconds that have since the device has started, and the end time is going to be the start time plus 1 second. So we can use that to check, have we reached the end time yet? So while the current time is less than the end time, we're going to do a calculation. So this is just an arbitrary calculation. Float, which is the result that we're going to get, result equals 123.56 times 7890.12, and then we're dividing that by 345.67. So there's a calculation there. Once we've done that calculation, that will take an amount of time to run, and then we're going to increment the number of calculations that we've done within that loop to get a number of how many operations have we done in that 1 second. That's actually going to run for the number of seconds that we have. So if we've got 3 seconds, it's going to do this 3 times. The total calculations is going to be whatever the results is from that calculations. We're going to add that to the total calculation. So every time it runs this loop, it'll increment that after it's run through that little loop there. And then we can then say calculations in the second, how many seconds we've run and how many calculations have been performed in that second. And then once that loop has finished, we can then say total calculations in 3 seconds is the total calculations. Notice that we have a print and a print line. Print will just print out and then not do a new line, whereas print line actually does a new line and returns to the next line underneath. And then we have loop, which doesn't actually do anything because we're only going to run this through once, so we don't actually have to have a loop program. So that's how we write it in C++. Now if we want to do the same thing, the exact same code in MicroPython, this is how we do this. Now notice how many lines of code there are there. I mean, there are a few blank spaces here, but it's 38 lines of code in total, whereas it's only 23 lines of code to do the same thing in MicroPython. And I think for me it looks a lot easier to read. So we're going to input the time. We're going to do number of total calculations equals 0, total, and then calculations equals 0. We didn't have to define what they are. MicroPython is clever enough to work out that because that is a single whole number, then that's going to be an integer. We print out starting the MicroPython calculation test. We run it for 3 seconds. So for second in range 1 to 4, because that will, once it reaches 4, that's where it would end. So it will only do 3 seconds and it starts at 1. Calculation equals 0. Start time is time.ticks ms. Then we do end time equals start time plus 1000, so run for a second. And while the time.ticks is less than end time, perform some calculation. I'm just going to hide my face there. Let me see if I can do that without, if I do that on the primary display. There we go. So what we're then going to do is run second in the range 1 to 4. We're going to do the calculation. We've just said that. While time ticks is less than end time, result equals, and then we do the calculation. We increment the calculations value and then we say total calculations equals plus equals calculations. We add that to our total calculations. We can print out this for each second that goes by, calculations per second, and then we can say total calculations in 3 seconds is total calculations. So let's go over to our Arduino. What I'm going to do is I'm going to click on the verify button. What this will do is it will compile the sketch, it will check for any errors, and it will actually produce that binary file for us. So what this is going to do is basically prepare that file ready for upload onto our device. Once it has finished doing that, and notice how long it takes to do this as well. So I'm running this on a Mac M1 silicon laptop. It takes quite a while for it to actually do. Now that that's complete, we can now actually upload that. So if I click on that, it's going to have to compile the sketch again, which just seems a bit redundant to me. It's going to compile the sketch again. Once it's done that, it's then going to upload it onto the Arduino. So if I go over to, let me see, over here, if I turn down the studio lights, see if I can do that. Let's go for the overhead light. Just so you can see like the flashing lights and so on. So you can see here it says uploading, it's finished uploading. That means that the little sparkle rainbow effect there means that the device is ready to go. And you can see there it's running. So it says starting C++ calculations test. Okay, so that was our test on there, so we can keep those calculations on the left hand side there. And what I'm going to do now, I'm going to go over to this bench and I'm simply just going to move this onto here. This is the one that's running MicroPython. So if I now come over to here, if I then just connect, I can connect to that particular modem there. And you can see now at the bottom there, we have our MicroPython up and running. So I can simply just run this speed test code and we can see on there how many calculations per second it's doing. So we had the C++ one doing 817,347. And on the right hand side, you can see there that we have 65,536. So MicroPython running this particular piece of code is about 12 times slower. I think it's 12.48 times slower. So that's the speed test. Let's get back over to our slides. So yeah, we did the speed test there. So debugging, if we want to make a change on our Arduino code, you've seen how long it takes for us to compile that. It's about a minute. So every change that you make to your code, it takes a minute to recompile that and re-upload it. So let's get back over to our environments. So if I come over here, I'm on the MicroPython one at the moment. So let's say I want to start out and I want to change that total calculations to 1. I can make that change and I can immediately run that code. So I didn't have to do anything else. I just click on the run button. So if I change that back, there we go. We can run that code instantaneously and we get our results. Now if I just go over and I swap once again back to our C++, and if I now want to go back over here, let's just grab this on the screen, and I want to make a change up here. So let's change that to calculations to 1. And I'm going to now upload the code changes. So you can see now the clock's ticking. It doesn't run instantaneously. We have to wait for the entire thing to recompile completely from scratch and then upload to the device. Whereas on the MicroPython one, it was instantaneous to do that change. Those amounts of time that it takes to check your changes and rerun it can really add up if you're developing some more advanced code than a simple speed test. So again, we're still just waiting for that compilation to finish there, upload, and now it's ready to go. So if you go and check that time that it takes to do that, it's not insignificant. And there we've got our code running. Once we've written the code, once the code is compiled, it does run much faster on the device. Okay, let's get back over to our slides here. So let's go for the Smackdown. Here we go. So these are some example pieces of code that we could write to demonstrate, to illustrate each of these changes. So precise timing. So if we want to demonstrate the difference between real-time precision on the C++ versus MicroPython, we can write two programs. One that will use this delay milliseconds on the C++ to blink an LED with very precise timing, such as toggling an LED every 500 microseconds. So this might be useful if you're doing some kind of persistence of vision, one of those spinning things where it shows an image on a display by rotating something around very, very fast. C++ will really be useful for this. Writing this in MicroPython, we can do time.sleep_ms or time_sleep_us to attempt the same task. And what we can see there is that the C++ has precise control over the timing, allowing microsecond level delays. MicroPython has some overhead due to the interpreter, so very small delays might not be quite as accurate. Measuring that drift over time, the Python interpreter will introduce a latency compared to C++. So that's going to give 1 point, I think, to... Let's move on here. 1 point to C++ there. Next up, let's have another battle. So memory usage with large arrays. So showing the difference between memory usage and efficiency. So if we wrote a C++ program to declare a large array of integers and manipulate that data in some way, we can measure how much static RAM is used using serial print line free memory. You can see how much memory that takes to store that. On MicroPython, we can do the same thing. We can declare a large list of integers. And what we'll see there is that because of the interpreter on MicroPython and the dynamic memory management, we'll likely see more RAM for the same data structure. But what you do get for that is a lot easier use of memory, so you don't have to free it up when you've stopped using it. MicroPython can take care of all that. But on C++, you have to directly manage that memory allocation yourself with things like malloc. So that's, I think, a point there to Arduino. Next up then is interrupt service routines, ISRs. So on this one we can demonstrate how interrupts are compared between the two environments. C++, we can use a hardware interrupt to toggle an LED whenever a button is pressed. In C++, interrupts can be handled with extremely low latency and no blocking. So we can assign that in the background. When we press the button, it will instantaneously make that LED light up. In the MicroPython, we can do the same thing with pin.irq. What we will compare there is that C++ is much faster because the code is running natively, whereas again the overhead, because of the interpreter on MicroPython, some limitations on what can be done inside the interrupt service routine in MicroPython may also apply. So we do get that kind of cost because of the interpreter. Now, in my experience with robotics, these changes they're so insignificant that it doesn't really matter, and therefore the benefit of writing code in MicroPython outweighs any kind of speed benefit. You're not really needing that if you're moving a servo about, for example. So I think that one is a point again to C++ because it's a speed one. Next up then we have complexity of math operations. So what we're going to do is compare mathematical computations, similar to what we just did in that speed test demo. So we can write a loop that will calculate the difference of floating point math operations, such as solving a trigonomic function or comparing some square roots repeatedly. And what that will show there is that the C++ floating point math will execute much faster because the code is pre-compiled into machine instructions, whereas MicroPython will execute the same operation slowly because each operation has to be interpreted one at a time. So I think that's again another point. It's not looking great here, is it, for MicroPython speed-wise? Pulse width modulation, signal generation. So if we want to make a servo move, we can create two programs to do the same thing. So C++ will use hardware pulse width modulation to generate signals with a frequency and duty cycle, such as controlling a servo motor or LED brightness. And what we'll see there is that C++ typically offers more precise control over pulse width modulation with access to the hardware registers and low-level settings. MicroPython can do pulse width modulation. We've done that plenty of times on the channel, but may introduce some delays and less precision due to interpreter overhead. So again, that's not looking great, is it, for MicroPython? Speed-wise, it looks like Arduino is almost winning the fight here. Power consumption and comparison. So In C++, we can use sleep modes such as low power.sleep or delay in combination with interrupts to minimize power consumption while the Arduino waits for an event to happen, such as a button press or sensor data. MicroPython has an equivalent machine.sleep or time.sleep, machine.deepsleep, but MicroPython doesn't support all the sleep modes due to the interpreter overhead. It might not be as low power efficient as pure C++. So one more time there, I think we've got the Arduino C++ in the lead there. It's working with serial communication, so if we want to do some I2C or SPI sensor communication, such as an OLED display, retrieving some data at a high pull rate, we can write a program to do that for both of them. We can use the MicroPython machine.I2C or machine.SPI methods, and we can use the built-in methods for doing that for C++, and C++ will likely have faster communication, more consistent timing. And again, for MicroPython I2C SPI handling is going to be slower because of the interpreter. It'll be more noticeable in the higher speed and time sensitive applications as well. So look at this, Arduino's in the lead there, 7-1 with MicroPython. String manipulation and data parsing. So we're going to write a program that can do some string manipulation and performance. So we can parse, and what we mean by that is like analyze the string. There might be data from a sensor, CSV formatted input, break it into different tokens and do things with it. MicroPython is amazing at this. This is one of the reasons it's really strong. String handling, string manipulation such as dot split, really quick and easy to do as well. So Python is inherently stronger at handling strings due to the rich set of libraries, but there might be a significant performance overhead in manipulating large amounts of data in MicroPython compared to C++. But this is one of the areas I think Python and MicroPython really leads ahead. So we're going to see a bit of a boost there, a bit of a fight back from MicroPython, 7-4. Arduino's still winning on this fight so far. File system access. So we can write a program that deals with reading and writing of files if the board has a supported file system. Now, you would have to actually bundle in on your C++ program a file system library so you can read and write to, say, an SD card. MicroPython has that kind of function built in, so we can just use open for that. So file system access is much simpler in MicroPython due to the built-in file handling functions. It might be a bit slower compared to C++, and in C++ the file system will be faster and more efficient for large file handling operations. But again, I think for me this is definitely a win for MicroPython. So 7-5 there. C++ is still winning. And the next one is development work speed. So the workflow, how long it takes for you to change code, re-upload that code to your device, test it again. So this is going to show you how much better MicroPython is, because you can make those changes immediately, instantly, and have that change immediately applied. So MicroPython excels in rapid prototyping because you can run code without recompiling. It easily converts into convenient because it's doing the interpretation, and you can use the REPL, the read, evaluate, print loop for instant feedback. C++ requires recompilation and uploading, which takes longer, and though it provides a high performance in the final product. So this is where the MicroPython does a sucker punch to C++ code there. So for me, the winner is MicroPython. It's not just about pure speed. MicroPython is the winner because it makes the art of programming easier to learn, more elegant to write, and quicker to fix problems. So come at me in the comments if you disagree on that. Is it just about raw execution speed, or is there more to software development than this? So if you want to get yourself one of these amazing hats to prove you're a real robot maker, you can check out our store, kevsrobots.com/merch, and grab yourself one of these hats. We also have hoodies and mugs and things as well. And if you want to join me on Discord, we have a Discord group as well. So if you head over to kevsrobots.com/discord, you'll find yourself a sign-up link there. And if you want to follow me on social media, I'm on all the social media networks. You can find me at Threads at KevMcAleer at threads.net. I'm on TikTok at KevMcAleer6. I'm on Instagram at KevMcAleer. I'm on X at KevsMac. I'm on Mastodon at KevsMac at mastodon.social. I'm also on Blue Sky at kevsmac.bsky.social. Now, before we end the show, I want to show you one last thing that we can do, which is really, really cool in MicroPython. So I'm going to bring up our MicroPython library here. Make sure I'm plugged in. And let's just connect ourselves up. And what I'm going to show you on here is how you can run MicroPython really fast. Let me just connect up to that one there. Okay, so let me open up some extra files here. So I'm going to open up Viper test. So there is this Viper, MicroPython.viper. This only works, I think, on, in fact, let's just swap out this to a different, I'm going to use a Raspberry Pi Pico 2, in fact. I'll just try connecting that up. There we go. Okay, so I'm on a Raspberry Pi Pico 2. Viper is a special decorator which runs code, and it has to be specific uses of code. I can go into this in a further show if you like, but it runs far faster. So if I run this code here, this is going to have a loop, and it's going to basically just add two numbers together. It's going to do it 1,000,000 times, and we're going to run that loop there 3 times. So you can see there, we're going to run that loop 3 times, and it ran the loop 3 times in 420 milliseconds, or is it microseconds? Milliseconds. That's ridiculous. That's very, very fast. But we can go even faster than that. We can do even one better than that. So let's open up ARM test. So MicroPython allows you to write assembly language directly in a MicroPython function. So you're operating at native speeds, basically. You're basically telling the, it still has to interpret each line, but it can do that at such a speed because it doesn't have to do any kind of translation. It can just make this directly into a machine code, line by line. It can run very, very fast. So we saw there we could run, was it 3 million loops in 400, or million loops in 420 milliseconds. Let's do this in pure machine code. It can do that in 27 milliseconds. So that's like orders of magnitude quicker. And all it takes is having this decorator on top, machine.asm, assembly language machine code thumb, and we've got these special functions here. So if you want me to do a show specifically on this, I can certainly do that for you, but this is how we can make MicroPython run as fast as, almost as fast as native C. So that's an extra little bonus for you there, if you're interested. This doesn't work on all MicroPython devices. If I tried running this on the Arduino Nano ESP32, I don't think their MicroPython has these optimizations in there, but this is running on a Raspberry Pi Pico 2. Just see just there, that has those optimizations built in. Okay, let's get back over to our slides there. So if you want to join me and help support the show, you can do that in a number of different ways. You can do a super thanks, the little thanks button that appears at the bottom of the screen there. I think they also have like a join button if you want to join the YouTube membership program. If you're watching this on live now, you can also do a super chat as well. Those things will pop through. Make sure I've got those switched on. Let me just switch on the stream elements. There we go. You can also just buy a coffee if you want to single one off, but all those links there, go to kevsrobots.com/coffee, you'll find all the information that is available there. Okay, and
you know you have an I Love MicroPython t-shirt with
yes,
and I Love C++.
That's very true. So I want to give a shout out to our supporters now. We did have somebody, I didn't have quite enough time to change this slide, but I think it was Littleback who also joined. Let me just make sure I give a shout out to all the right people here. Let's go to YouTube Studio. I've got a second monitor over here I'm just having a quick look at. Let me just find that. So we had Sebastian buy a coffee. He bought 2 coffees. We have Maria Louise Mayer bought 3 coffees in the past month, and we've also got Toxic Toad who bought a coffee as well. So I'm just trying to find on the other side just there. Yes, Littleback, who's also a member on the YouTube side. on the Buy Me a Coffee side, so we've got Shemi, we've got Alvaro, we've got Marie, we have Jeff, we have Steve, we have Dean, Corty, Marley and Tom. Thank you so much for supporting on the Buy Me a Coffee. And then over here on the YouTube membership side, so we've got Littleback, we have Bello, we have Dale from Hybrid Robotics, Oxrad39, Littleback, we've got Ford, we have Paul, Johnny, we have Handsome Cheerlight, Stephen, John Paul, we have Alistair, Cassie, Tinkering Rocks, Johnny, Michael, and of course we have Tom as well. So over here we should have YouTube suggesting another video over here that you should find interesting. Please click on this video, let me know if these are of interest to you, and yes, I shall see you all next time. So I've got to go back and stitch the two parts of the show together because we had a bit of a glitch midstream, but if you're watching this on the recorded version, you might be able to find the actual split, so points if you can find out exactly what minute that splits at and say in the comments. So yes, at this point in the video I'll say thank you so much for watching, and I shall see you next time.